Okay, so last time we talked about this fracture toughness testing of metals. We have talked about the four. This is the societies, and one is ASTM, one is BSI. BSI means British Standards Institution, ISO International Institute of Standards, JSME, the Japanese Society of Mechanical Engineers, and these are four commonly used these standards. So you should know that. Okay. We also talk about the general consideration for the specimens, and we have, and we also talk about the five commonly used specimens. And one is called a complex specimen. Second one is a disc shaped. Third one is single edge. And the fourth one is a middle tension. Is a central crack. And the last one is the arc-shaped specimens. So this is what we talked about last time. And in addition to this, we also talk about the testing methods, testing machine, loader cells, caliper gauge, LVDT, along with this potential drop technique. So we have talked about this. And then I stop there, and now today we will continue our talk. And we can also use the upload, the unloading, the compliance technique, and to check the crack growth. The crack growth can be inferred from the load and the displacement transducer. So where we can get this one, because and we know that for this figure, right? And for this figure, guys. So for A1 is from A1 to A4, the crack grows. I want you guys to follow me closely. All right. So from A1 to A4, the crack is growing. And we know that the higher the crack, and the easier with the same load, you can easily get the same displacement, right? And or you can just see that, for the higher the crack, is more compliant the specimen will be. As a result, if you use even low, it's very, very low, this is load, and you can get the same displacement. Okay? Or you can just suppose we use the same load. If we just use the same load and we just extend all these lines, you can see A1 has the least displacement. A4 will have the maximum displacement. You guys agree? Why? Because we know A4 is greater than A1. As a result, the specimen becomes more compliant. More compliant means that it's much easier to be deformed. Okay, so for this one, this figure shows us we have different crack. We have different specimen. For each specimen, the same material, geometry, everything is the same. The only difference is the crack length. And for this case, we need to have 4 specimens. Okay, 4 specimens. In order to minimize the cost, that means we can reduce. This is the specimens, right? We can reduce specimens. How can we reduce the number of specimens? We can just do the load and the displacement, this relationship, and go there. And then whenever we have a crack at some time, and we just do the unloading. Okay, guys? We just do the unloading. For this is unloading, so this one, and so this one is unloading the crack. This corresponds to the crack A1, very small crack. So you will have the slope, right? So you have this slope, and then you just loading again back, and then keep loading, and then do unloading at the next point. If you do this as unloading, and you will find that because the crack is growing, right? The slope, the stiffness of the specimen decreases. As a result, so this guy, the second unloading slope will be smaller than this one. So as the time goes, you continue to do these kind of things, and you will find that from the very beginning to the very end, you will find that the slope becomes smaller, smaller, smaller. So this figure and this figure, we are using the same principle that as the crack grows, the compliance of the specimen decreases. So the difference between these two, the figures, is that this one, we need to use multiple specimens. So economically, it's not good for us. But for this one, we only need to use one crack, one specimen, but we will measure loading, unloading. We will carry out loading and unloading continuously as the crack grows. So economically, this one is feasible. You understand, guys? I might ask you guys in the final exam, I might give you these two figures, and I will just show you these two figures and ask you guys to use your own words to tell me what this figure says and what that figure says, and why, how they are different, and what kind of benefits we can have if we use that figure instead of this. So this is one important thing. Second one is a side grooving. So here, this is a specimen. Okay, this is a specimen, and usually we need to do the before we conduct the experiments, and we need to do the side grooving. Side grooving means that so this is side grooved the specimen. Side grooving means that at this location, we just cut this specimen longitudinally. Okay, not longitudinally, transversely. For this case, horizontally. And this is, we have cut this side and cut that side. So this is a triangle. If you see from this perspective, this guy is a triangle. And you just remove this part and remove the other part. So this is our original with the thickness. So this is the BN, and N means notched. Right? Notched means that we do side grooves. Can we now? BN means notched width, not notched thickness. So why we need to do the notched thickness? I'm also very, very interested in this one. The significance. What is the significance of the side grooving? So you guys might have might do this work. Either you go to the graduate school to pursue your master's degree, or maybe even your doctoral degrees, or you just go to the industry, okay? Because you guys mechanical engineers and Carlos is aerospace engineers, you might do the same thing, do these kind of things. And your boss will ask you, Carlos, please, we want to take this, I will have new material. And you need to think a way to determine these guys, the toughness, fracture toughness. How to do that? Carlos, give you 7 days. Give me a plan. All right? So you need to see, hey, talk about this one before. Just go back to look at my lecture notes. And then you know that. You need to tell your boss. If your boss is really expert in the fracture mechanics, and he expects that you tell him or her that this side grooving is necessary. Okay? If your boss does not know that, you need to teach him or her. And he or she will be very, very impressed. Bobby.
Why is it so necessary?
Okay, I'm going to tell you.
Oh, okay.
So why it is necessary? So because this is a side effect. Actually, this is a side effect on this surface and that surface. And in this direction, they do not have the stress, right? They're stress free. As a result, they are low triaxiality area. Not in this, for this region, its triaxiality is very, very low. And also at this edge, the same thing, triaxiality is also very, very low. What is the triaxiality? triaxiality means that in three directions, x, y, z, and you must have the stress distribution. However, because the side effect, we know that before I set group 8, on this side, traction free, right? Empty, is void. On that side, also void. On this void side and on that void side, no stresses in this direction. You guys agree? As a result, triaxiality is very low. This is triaxiality. So in English language, whenever you see the tri, what comes into your mind is? Three, right? Tricycle, triangle, all these kinds of things. Triaxiality means the three directions of this is the stress. X, Y, and Z. If one side is the empty or just as a boundary surface, you need to know that triaxiality is low. What will happen to the triaxiality will low when this deforms something before the side group, okay? So this guy will come out. Right, so this is what I wrote. The primary purpose of side grooving is to maintain a straight crack front during the R curve testing. And we know that. What is R curve, guys? Can somebody tell me what is R curve? So you are raising your hand.
No.
Yeah, try to answer this question. What is R curve? R means resistance, right?
Yeah.
The resistance curve. Resistance curve. So how resilient and how resistance, what level of resistance so this material can have when you crack it. This R resistance curve. So straight front means that this is a crack. You can see this is a crack, right? This is a crack. Let's look at my hand. So this is a crack, right? When I open it, the crack, this is my crack hand, crack front. The crack front go from here and to this way. You guys agree? So this is a crack, right? So this is with my crack front. So at the very beginning, this is a crack, it goes in that direction. That is a crack front. A specimen without a set groove is subject to crack tunneling. So here is a crack tunneling. Crack tunneling means so this is very this is a tunneling. Right? This is the tunneling. The crack, the tunneling. So you know tunnel, right? And the shear lip, the forms. The shear lip. You can see on this edge, we have shear lip. And because the material near the outer surface, on the surface means that on this edge, is a state of low stress triaxiality, as I told you guys, right? For this surface and that back surface, in this direction, no stress. Yes, makes sense, guys? No stress means that in this direction, no constraints. And the side groove remove the low triaxiality zone, this area, and if done properly, lead to relatively straight the crack front. And straight crack front is this line. If you just go this way, right? So the typically side groove fracture Taiwanese specimen and have a net thickness, and we call it net thickness or notch thickness, and BN is about 80%. So know that, okay? And BN is either the net thickness or the notch thickness. Questions so far? Guys, did you see this one? You can see. So I want this to go very flatly go here, but now I have a crack tunneling, and also here is the this is the shear lips. So what I want to know is that, and why we need to do the side groove. And what is the bottom line to do the cell group? You know that, right? Guys? Are you listening to me? Okay. So if the cell group are too deep, they provide lateral singularity, and it's too deep. That means it goes so from this ligament is too short, and they have lateral singularity in this direction, and which causes the crack to grow more rapidly as the outer edge. So this is if the cell group are too deep, it is very bad also. Any questions regarding this cell group? Questions regarding this cell group? And I might ask you what is crack tunneling and what is the shear leaves? And then we talk about the KIC testing and how to do the KIC. And because we know that the most important, our first and also the most important concept in the fracture mechanics is Ki, right? So this is opening mode and stress intensity factor. And KIC is the critical stress intensity factor for opening mode, and which is the material parameter. And how to do this KIC testing? And because we are working in the US, and we use ASTM. Okay, so for the British people, British researchers, or this is students, professors, and they use British Institute of Standards. But here, and we use ASTM because it commonly recognize the standards that we need to follow. So this ASME, ASTM E399. So this is a protocol, right? So you can just all the ASTM the protocols, and they are free and they are posted online. Whenever you need to use a protocol, and you can just download for free, and then you can just prepare your specimens accordingly. So this is a KIC test. For this one, and in this protocol, we have 4 configurations: the compact, ICNB, arc-shaped, and disc-shaped. And for this one, we do not have the 5th one. The 5th one is the tension. This is middle tension. So it is it's called this middle tension. We have a central crack. And for this is E399, we have only 4. Okay, you should know that. And so for these 4 guys, we need to make sure the width equals 2b. And what is the b, guys? And b is the thickness. All right, the b is the thickness. The w is the width of this specimen. And we also know that the crack length, and over this w, the crack length over and this w is about 0.45 to the 0.55. So you need, whenever you want to use this protocol, and you must prepare your specimens accordingly. Okay? If you do not follow this one, and after you finish the testing, and the people will question the validity of your results. Why? Because you do not follow this closely. So thus, the specimen design is such that all of the key dimensions, crack length, this is the width, W minus A, so W minus A is the length of this ligament, are approximately equal. So this design results in the efficient use of material, since the standard requires that each of these dimensions must be large compared to the plastic zone. And we know that, right? Because for the KIC, in order to have valid KIC, and so A, W, and B, they must be bigger than the plastic zone. Otherwise, the KIC you get is invalid. That is the assumption. And the KIC, make sure it is in a state of the principal strain. And the KIC, whenever you want to test the KIC, and you need to make sure it is in the state of plane strain. What is a plane strain, guys? Physically, when I say this plate is in the plane strain, and physically, what do I mean? What can you imagine? Bobby,
A very large plate with infinite thickness?
which here we say the decent thickness, okay?
Okay.
It cannot be very small. For example, for this sheet, okay? For this sheet is very thin. So this is a typical plane stress problem. You understand, guys? This is a typical. So you can see this is a paper sheet. This paper sheet is very thin, right? You guys agree? Don't use the microscope. I'd say just use our eyes to see. It's very thin when compared with in plane these dimensions, the length and these widths. The thickness is very thin. So this is a very typical example of plane stress problem. A plane strain problem means that the thickness is decently large. Why this one is important? Because we need to make sure so we have a 3D stress state. Can you write down? Why we need to have plane stress, plane strain, instead of plane stress? Plane strain can ensure that we have a 3D stress state. So here are some these observations. So even though plane strain, that means the thick plate is a necessary condition for valid KIC test, but it is not sufficient. Right? And so this PE principal strain is not sufficient. And a specimen must also behave in a linear elastic manner. That means we should not have decent the plastic zone. If we have different plastic zone, KIC is invalid. So the validity requirements in these standards are very stringent. You can see very stringent. Because even a relatively small amount of plastic deformation invalidates the assumption of K theory. So be very, very careful. So for this is the principle, for this is the protocol. So this protocol is the earliest one, it's well established one, but it is too stringent. Right? Because at the very beginning, when people define the protocols, people tried to consider all the case scenarios. Right? You guys agree? And to be safe, for safety reason. So the size requirements, and we need to have these size requirements, B and A, and 2.5, and KIC. KIC is a stress intensity, critical stress intensity factor. And what is the sigma y guys? What is the sigma y here?
Yield strength?
Yield strength. Right? Sigma ys here is yield strength, and which is also a material parameter. So also the ratio of A to W and is located between 0.45 and to 0.55. So keep in mind, so these two inequalities must be holding. Otherwise, and your results is questionable. Questionable means that, and when people wanted to mimic your results, but if they follow this procedure closely, however, you did not follow this procedure closely, and your results might be totally different from other people's results. Okay? You have sense? Even though everything else is the same material, same geometry, everything the same, but so if this is not followed, and your results will be questionable. So K maximum at the very beginning, at the less than 0.80 KIC, and final stage less than 0.60 KIC. So this must be satisfied. Also sigma ys, okay? So this is sigma ys1 yield strength on the temperature at temperature 1 and the pre-cracking edge. So when you pre-crack it, so this is a temperature 2. So this is the tested at. So this is temperature when you test at. So we talk about this figure. We have PQ here. PQ is a critical load, and you can see how many modes we have, guys. Can somebody remind me? How many types?
3 modes.
Yeah, 3, right? Dylan, what are these 3 modes are?
That's opening,
Yeah, opening. Huh?
carrying,
Yeah, tearing is the third one. Which one is the second one?
shear,
Yeah, shearing. Yeah. Opening, most commonly one, shearing, and tearing. And tearing is out of the plane, right? So these are the 3. If we do this kind of testing, so load, if we have load and a displacement, and we will have different figures, and have different figures. And for this type 1, right? For type 1, and we just have 5% secant. This is this line. So this line will intersect. So this is original bold curve at this PQ, at this P5. We call P5. So this P5 is denoted as PQ. And keep in mind, and we will use PQ later, okay? And write down. So you do this. What you need to do is that you do the experiments and you have this load and displacement curve. This is for type 1 or model 1, is for type 2 or model 2, is for type 3 or model 3. For these 3 case scenarios, and we use different ways to get PQ. Right? For type 1, and we use a secant 5%, and which intercepts with this original bold curve, and this is a PQ. So this is our PQ for type 1. And for type 2, we use the type 2. If you do the type 2, and you will have this curve. And you will here, and the PQ is denoted as the pop in here. This is PQ. And for the model 3, model 3 is quite, this is a straightforward. I'm going up and then down. So for type 3, we just denote the PQ as a maximum. Okay? So some students might ask, Dolma, how can we get these 3 curves? If you have a crack, okay? If you have a cracked specimen, and by following different modes, and you will get very, very similar the curve, load versus displacement. Make sense, guys? Make sense? So as I said, you might be given the first task to do the toughness testing for newly developed material for your full-time job, or when you step in the graduate school. So after we get a PQ, okay? After we get a PQ, and then we calculate this is crack front. So how can we calculate the crack length? And we know that we have the thickness, right? I told you, we have the thickness, right? Right, guys? We have a thickness. Sometimes this is the crack front. This is my original this line. So at different locations, we will have slightly different this crack length. Do you guys agree? Because experimentally, we cannot ensure that our crack front is totally parallel to this initial starting line. That is impossible, okay? If you get totally parallel at all times, so other people want to see your data result, data. You know what I'm saying? Because the material, when people build the material, the forge the material and to get the material, and there is a lot of variability. of this same material. So to be safe, we measure the crack length at 3 different evenly spaced locations, and then we just get this average. And we use average crack length to denote the crack length at this point, at this instant. You understand, guys? Huh? Are you guys okay? And then after we get the PQ and we also get this A, the W is given, and we can use this equation and to get the conditional toughness KQ. So FAW is a dimensionless Bragg function of AW. It is given in polynomial form in the protocol. Right? This protocol we are using ASTM E399. And for the 4 specimens, they are compact and SEB single edged and arc shaped and also the disc shaped. And for these 4, individual value of FAW are also tabulated in ASTM E399. So, and what you need to do is you just check E399 online and to get this is F function. As I said, for different specimens, so F function is different. Okay? After you get this KQ, this is called conditional toughness KQ. It's a valid KQ result only if all valid requirements in the standards are met. That means if all these guys and they are met, then your KQ will be the KIC. You understand, guys? Does that make sense? Yes. Okay, so because the validity requirements, the KIC testing for this protocol, the ASTM E399 is of limited value onto structural metals. As I told you guys, the requirements is too stringent. The toughness and the thickness of most materials precludes a valid KIC results. That means usually the toughness and thickness cannot satisfy all these validity requirements. And if, however, a valid KIC test can be measured on a given material, it is probable too brittle for most structural applications. So this is the shortcomings. These are the shortcomings of it is the well established, commonly used ASTM E399. So when attempting to measure fracture toughness using this one, which is too stringent, and one runs the risk of invalid results due to the stringent size requirements once a result is declared invalid. So E399 offers no recourse for deriving useful information from the test. Right? So then people developed a new one. A more recent ASTM standard E1820 provides an alternative test methodology that permits valid fracture toughness estimates from supposedly invalid k-tests. So E8020 provides an alternative test methodology. Okay, so E8020 relaxes the specimen geometry requirements somewhat to some degree. It is a generalized test method for fracture toughness measurements, combining stress intensity factor, J integral, along with crack tip opening distance in a single standard. Any questions? What I want you guys to do in the final exam, even though it is the take-home exam, I might ask you guys, suppose we have a new material. I want you guys to use your own words to tell me how can we use the well-established, mostly commonly used, but too stringent the protocol E399 to calculate this is to not calculate this experimental mechanics to experimentally get the KIC. I want you guys to know that. What? Even though this is, I just give you hypothetical material, but I want you guys to know that, at least the steps. And then he ask you to make some comments. If this is E399 is good, and yeah, it's good, but it is requirements are too stringent. And then, are there any alternatives that people can use to avoid these kind of sometimes unnecessary but too stringent disease requirements? And then you tell me E8020. Okay, guys? You understand, guys? As I said, even though this is the take-home exam, but I want you guys to follow me closely. You know, whenever you see a question from me, and you can immediately know that where I taught it, and then you just look at lecture notes, and maybe the lecture recordings to know on when and where I taught, and what details I have covered. Right? Right, guys? So do you guys have any questions for me? No question? Yeah, for the homework 4, that do your best to do something. Alright, do your best to do something. But the next Monday I'm going to talk. But before I talk, I don't want you guys to just accept this information, receive this information from me passively. I want you guys to take the initiative, look into these problems first, to see independently how you can solve the problems. Right? Even though you know that I'm going to talk about all these problems, but I want you guys to think about this ahead of time. So, any other questions? If there's no any other question, and I hope you guys have a wonderful weekend. We have a weekend again.